Yes,
Yeah.
yes, it is.
So the agenda of today's session is we will discuss a brief overview of Jtag interface. So Jtag is nothing but Jtag stands for Joint Test Action Group. So it is a interface for connecting our FPGA to our system for programming the bit stream or to configure the FPGA. And we will see how what is a part number of an FPGA, like what the part number actually says. So it's not just important. Just we should have a basic idea about the part number. Okay. Next, important files in the generation in the programming of FPGA like bitstream file, programming file, MCS file, and constraint files. And afterwards, we will see the architecture of a microblaze processor. So it's a AMD FPGA. So in this FPGA, we will be having our soft core processor as well as our PL. We will see what is it. And this is Arty A7 FPGA. It is a beginner board. Using this board, we can generally build small projects, or it is also used for testing some process. Like we can also use it for major projects also. Yeah. So this is the agenda for this session. So coming to this JTAG, it is Joint Test Action Group interface. So in previous session, we have seen using the Vivat tool, we are generating the bitstream file, right? So we are generating the bitstream file, that is dot bit file. So that file, if we want to store it into the FPGA so that our FPGA can be configured, so what we are going to use is JTAG interface. So using this JTAG, actually we can program our FPGA, or we can actually configure our FPGA. That is, using this JTAG interface, it will be a hardware. If possible, I will show the photo if no copyright. So I think there will be no copyright issues in that if I upload in YouTube, or else you can just simply type JTAG in Google, and you can see the picture of the JTAG. So one side it will be a USB connection, so that you can connect it to your system or PC, and other side it will be a set of pins, so that you can connect it to your FPGA JTAG interface. So with the help of the JTAG interface, what you can do is the created bit file can be loaded into the FPGA. The created bit file can be loaded into the FPGA, and your FPGA can be configured according to the logic you have written in Verilog or VHDL. Okay. So this is the usage of JTAG. So a standard interface for programming and debugging. So you can also use JTAG for debugging purpose also. That is, you can test your code whether it is working or not without writing any software code. So what is the process is generally is like this will be your FPGA. This will be your FPGA, and you will be having one processor. So this processor is responsible for communication of all the peripheral devices like UART, I2C, or any other Ethernet. So if you want to access any data through this I2C or Ethernet or UART, the data which has been sent through these peripherals into, you want to access these peripherals using the FPGA, you should have a software code actually. Okay, you should have a software driver or software code which is written in C++, uh, generally. So this driver is used for is written for this processor, like how this processor should communicate with this peripheral devices, and this processor code which is written inside this software will communicate with this I2C, Ethernet, and UART like peripherals, and it will capture the data, and it will process the data, and using AXI interface. So generally using the AXI interface, the processor will communicate with the FPGA. Okay, this is the process. Once again, I will explain this. So the driver code or the software code which you write for the processor, that will help the processor to communicate with the peripheral devices like UART, I2C, Ethernet, or any other peripheral device, and the processor will fetch the data, and or from the or from the memory. Okay, so it will fetch the data from there, and it will access the data, and to send the data to the FPGA part, we will be using AXI interface. So using the AXI interface, the data will be, or the processor will be communicating with the FPGA. Is this clear? How the processor is communicating with the FPGA? Is it clear? Yeah, I hope it is clear now. Coming to this, Jayvardhan, can you please mute your audio? Hello. Yeah. So the usage of Jtag is, it connects through a Jtag cable to the FPGA development board. Common tools used for is Xilinx Impact and Intel Quartus Prime program. So using this, we can configure our FPGA. Next, how to read the part number of the FPGA. So for reading the part number of an FPGA, so the FPGA part number will be, for Xilinx devices, it will look like this. So X represents a Xilinx device, and so XE7A100T so indicates the FPGA family 7 series. So 7 represents the 7 series, and the model is RTX A7. Here A represents the RTX A7, and the device is 100T. So here 1 represents the speed grade, and CSG 3 to 4 is the packing type and pin count, and C is the temperature grade. So like this, for different devices there will be different part numbers. So for different FPGAs there will be different part numbers. So with the help of the part number, you can actually differentiate different FPGAs. Coming to the some important files in this FPGA. So one is bitstream file that we have already seen our previous session. So it may be a file extension of .bit or .bin. Okay, this file, after creating the bitstream, so in Vivado tool we have seen, right? So after clicking the generate bitstream file, so this file will be generated and it will be stored in our local directory where we have created that project. Okay, if possible I will show today, or in next session I will show where it is getting stored. So there will be a file called .bit file or .bin file that will be stored in the project which we have created. So this is the primary file used to configure the FPGA. So this is the file used to configure the FPGA, and the bitstream file contains a binary data that defines the logic and routing configuration of the FPGA. This I have discussed in previous session, right? So this file is used to actually configure the routing paths between the different LUTs in the FPGA. And we have one more file called programming files, or .mcs or .hex or .js, etc. So before this, I want to explain one more thing. So before this, I want to explain one more thing. So this is our FPGA, and let's say we have two memory devices like this. Let's say this is our SRAM, and this is our let's say flash memory. So this is non-volatile, and this is volatile. So do you remember the difference between the non-volatile and volatile, which we have discussed in our previous session? Anyone? Any idea of this? Non-volatile and volatile? Yeah. Okay. Let me tell you. So coming to this volatile, as we have discussed in our previous session, so volatile devices can retain the data even if the power supply is removed from the device. So the data which has been stored into the flash memory will retain the data information inside it after removing the power supply also. Whereas coming to non-volatile devices, the data information which has been stored inside this SRAM will not retain if we remove the power supply. So if the power supply is removed from this board or FPGA board, the data which is present inside this SRAM will be removed, whereas the data which has been stored inside the flash memory will retain even if we remove the power supply. Okay. Now, after creating the bitstream file, which we using the Vivada software, the dot bit file has been created, right? The dot bit file or dot bin file. This file we will be either storing inside this SRAM or we will be storing inside this flash. Okay, do remember this. So the bit file or the dot bin file which we have created, that we are going to store inside this SRAM or flash. So if you want, like if your purpose is to just test the FPGA multiple times, that you will write a code and you will check the your code is working correctly in hardware or not. So if it is not working to your expectations, then you will modify your code and again generate a bit file and again you will load it into your hardware, right? So multiple times if you want to test your code inside the hardware, then what you will do generally is you will store your bit file in the SRAM so that you can easily so that you can multiple times you can check your code whether it is working correctly or the hardware is responding according to your behavior or not. Okay, so in these cases you will use SRAM, and after finalizing your code and if it is working fine in your hardware and hardware is behaving as like you expected or like you wanted, then you can store that bit file into the flash. Now what happens, this FPGA will communicate with this flash, and the configuration of FPGA is happening with the bit file that is stored inside this flash. Both cases, when you have stored the bit file in SRAM, the configuration of FPGA is happening using this bit file stored in this SRAM. Okay, so when you are storing this bit file in both cases, like when you are storing this bit file in SRAM, it will be stored in the format of dot bit or dot bin. Okay, whereas when you want to store that bit file in flash, then you will generate a file called .mcs. Okay, .mcs. In case of Vivada I'm talking, so you will generate a file called, this is also a bit file, but if you want to store it in a flash device or flash memory, then you will create a file called .mcs and you will store it into the flash so that the bit file will not be erased at all. If you want to erase only, it will erase, or else it will not at all erase if you remove the power supply. So that what happen, if you power off and power on, that bit file will be restored and the FPGA will work according to the code which you have written or the bit file you have generated. Okay, so these are the two files. So programming file, so the second case, these files are used to store the bit stream in non-volatile memory such as flash. Sorry, my mistake. So flash is a non-volatile and SRAM is a volatile. Okay, sorry. Non-volatile means where the data is not at all erased, whereas volatile means the data is erased when we remove the power supply. Sorry. So these files are used to store the bit stream in non-volatile memory such as flash. So that can be loaded into the FPGA on power up. So different vendors and tools may generate different types of programming files. Okay. So is this clear? These two types of files, is it clear? No. Coming to the constraint files or .ucf and .xdc. So these files specify the constraints of the design, such as timing constraints, pin assignments, and placement constraints. So these are used by the synthesis and place and route tools. So what are these constraint files actually? So let's say, so this is Arty A7 FPGA board. So these are the switches. Okay, these are 4 switches available in this board, and these are push buttons. So if you have written some code in your FPGA, so in your Verilog, if you written some code that if you push that particular button, one LED, so these are 4 LEDs available inside this board. So if you write something in your Verilog code that if you press a button, then this particular LED should glow or it should turn off, like that code. So you want to connect this particular button with your code. So if you want to integrate this button with your code, so for that, what you will do, you will write a constraint file. So there will be a file called constraint file. So in that you will mention what are all the buttons you needed in your design. So or what are all the push buttons or switches you want inside your design. Or else you can also mention any type of timing constraints also in your file. Okay, so these constraint files are used for this purposes, and they are used by the synthesis and place and route tools. So these constraint files are used by synthesis and place and route tools. Okay, so these are the constraint files, and using the Vivado we can write these constraint files and generate the constraints for our design. Okay, I will show that in the upcoming sessions, like how we are going to write these constraint files. Okay, so this is the architecture of AMD Microblaze. Okay, FPGA. So this is a 32-bit processor core. So this is a soft core processor which is having. So it is connected with a JTAG, and we have SPI controller, I2C controller, UART, interrupt controller, timer, GPIO, general purpose input output. So these are some of the peripherals which are present in it, and DDR controller. Yeah. And this is our programming logic here indicates it is our FPGA fabric. So these two are connected, so the processor and FPGA are connected using the AXI interface. Okay, so this is a general overview of a microblaze processor. So this is our Arty A7 FPGA. So I will be considering this FPGA in my future sessions. So using this, I don't have any physical board present. So what I'm going to do, so in our when we are creating FPGA, when we are going to create a Vivado project, we have to select any part number, right? So I will be going to select this part number, and I'm going to write the code according to this part number. So that's why I'm showing this. So this board I'm going to select. So these are the so I will briefly explain what are the components available in this in this board. So here there will be a LED which is used to indicate whether the FPGA is programmed or not. So after storing the bit file into this board, the the LED this LED will be glowing. So if there is no bit file loaded into this board, this LED will not glow. So basically this LED is used to uh, indicate whether our FPGA board has bit file loaded in it or not. And this is USB connection actually, which is also known as shared USB JTAG or UART port. So using this actually in other boards there will be JTAG interface pins like this. So with the help of that we can connect, and this in this board what you can do is using a simple USB connector you can connect this with your PC. So this will act as a JTAG. Okay, so this will act as a JTAG interface. So using this USB connection you can program your bit file into this FPGA. And this is Ethernet port connection. You can connect your Ethernet, uh, and this is for power supply. And sixth one is it is used to indicate the power supply. Like if you have connected the USB port, then the board has power connection or not, it is used to indicate. And these are LEDs, this you can program, like, and these are slide switches, and these are push buttons. And we have, this is our FPG, this is our FPGA chip, microplace. Okay, so I have discussed in our previous session, right? So the microblaze will be a soft IP core. Soft IP core means there will be no hardcore processor present inside this chip. Okay, so the soft IP core will be present inside this chip. Now this is DDR3 memory. And coming to our flash, this is our flash. Okay, so these are the important components which we need to know inside our Arty A7 board. Okay, so is this clear for everyone? So in our upcoming sessions we will see how to write a code and how we are going to include this FPGA in our Vivado, and how we are going to program I will show. Okay, So yeah, so that's all for today's session. So if you're having any doubt, you can stay and ask, or else we can end the session. Thank you.